Friends, welcome to this class. In last class we saw about SN1, SN2, E1, E2, EL, everything we have seen. So let us discuss the distinguish between SN1 and SN2. What kind of compounds gives SN1 reaction and what kind of compounds gives SN2 reaction. See here, this is nothing but methyl attached to halogens, right? So this is a primary carbon, right? See here, carbon is having 3 hydrogens. Methyl means carbon is having 3 hydrogens and 1 X group. So primary carbons will always give SN2 reaction. So it will 100% give SN2. So it will be excellent here. And this won't give SN1 reaction. Right. So it will give SN2 excellent. Excellently it will give SN2 reaction, not SN1 reaction. See here also it is primary carbon, no doubt. But instead of 1 hydrogen to this carbon, I have replaced by a bulkier group. R means any alkyl group, right? So bulkier group I have instead of hydrogen I have put bulkier group, right? So it will give SN1, it won't give SN1 reaction. It is bad. Here also bad. It will give SN2, but SN2 not as that of like this compound. Here it will be excellent, but here it will be good. It gives SN2, but not as that of the above one, right? So in secondary we need to see the solvent effect, everything we need to see. But see here, if these are not that bulkier, then it may give SN2, right? Good. Let me write. If these are bulkier, then it will give major will be SN1. It will also be good. Only based on the size of this R group. If size is very high, it will give SN1. If size is very less, no steric hindrance, then nucleophile can attack from the back, so it can give SN2. Right? But majority will be SN1 because once it forms carbocation will be there, that will be stabilized however, right? So in tertiary element is excellent for this SN1. Excellent for SN1, but for SN2 it is very bad. It won't react, so bad. This neopentane, bad for this also, bad for this also, SN2. Because see here, this carbon is primary, no doubt, but it has got steric hindrance. 2 hydrogens will be there and this bulkier group. So the incoming group, that is nucleophile, will repel. Because of that steric hindrance, it gets repelled, right? Whereas this, if it undergo E1, there should be formation of carbocation, then alkyl shift should be occur. So some temperature, everything, solvent effect we need to say. So both will give bad at room temperature, right? See here once it lose this X with electron density, this carbon gets positive charge. That will be stabilized by this pi bond. So good here. And what with SN2, if nucleophile is there, if it attacks like this, it will leave. So it is also good here. So like these compounds, we can see both SN1 and SN2. Here also both SN1 and SN2. Good. Good. Why it is? Because if it leaves with electron density, this carbon gets positive charge, no doubt, and this positive charge is stabilized with this aryl group. Aryl means nothing but phenyl group will be there. Pi electron density will be there. That will be stabilized this carbocation for SN1. For SN2, the nucleophile will attack. Oh yeah, one more thing. Here for SN2, it will not be that good. Little less okay type. Why? Because of steric hindrance. See here, aryl means big group will be there and 2 hydrogens will be there. So if greater the size of this aryl group, it feels steric hindrance. So okay type. And here it will be excellent for this. Excellent for SN1 because here once it goes with lone pair of electron, I mean electron density, this carbon gets positive charge. This carbon will be stabilized by this lone pair of electrons here. So it becomes R O plus, it will be having one lone pair as usual, double bond this carbon. Carbon valency you need to satisfy, right? Carbon valence is, in these compounds we won't show that hydrogens. So hydrogens, valence should be satisfied. See here, 2, 4, 6, 8. So being positive, it is satisfying octet rule. So that compound is stable. So this carbocation is stabilized by this lone pair of electron. So excellent. It may give SN2 only based on the size of this R group. If R group is very high, then it will be bad SN2 reaction, right? See here. Here if it moves with electron density, then it will get positive charge. And this group is an electron withdrawing group. So positive, no possibility. So it will be bad, very bad. Or I can say no SN1, but possible. SN2 is possible, but little bit. Here also we need to see the steric hindrance. Bulkier group are there, steric hindrance will be more. So we won't get SN2, but possible. Possibility is there, right? So here also, see here it can't be possible and it can't be possible. See here also steric hindrance, 3 methyl group and bulkier group. So no SN2, SN1 not at all, because it is electron withdrawing group. So it is also having electron deficient. If this carbon also becomes electron deficient, how can it happen? So it won't leave that electron density. It won't leave that leaving group, right? So no SN1, not SN2. And here, if it leaves with electron density, positive charge will come. And both positive charge can be stabilized by the lone pair of electron and here lone pair of the nitrogen. So only SN1 and SN2. Possibility of SN2 is also there, but see here, if here steric hindrance would be little more compared to this way, so here less, product will be less than 5%. Here the product will be 10%. So like this. In this way we can distinguish between SN1 and SN2 based on the nature of these groups and also the size of the substitution to these carbons, and also we need to see everything, right? This is the difference between SN1 and SN2. In next class we shall see difference between elimination and substitution, right? Thank you.